Okay, how we doing? Welcome to our last Energy Law Lecture Series event for the fall semester. I'm Bill Keffer, and I am here on faculty at the law school and also the director of our Energy Law program, which includes this Energy Law Lecture Series. Those of you who have been with us during the fall semester might recall that we've had Jim Wright, who's chairman of the Texas Railroad Commission. We've had Charles Weller, who is with the CO2 Coalition. And both of those lectures are available on the Journal of the Energy Law Practitioner website, which is ttujelp, ttujelp.org. You can click on to the tab that talks about Energy Law Lecture Series speakers, and we've got them all there dating back to when we first started this in 2014. So you've got probably 60 plus speakers on various topics. But the most recent, I know Jim Wright's up, and I think Charles Weller will be up in the next few days. And this one today will be up on the website later as well. So if you can't make it today for some reason or didn't make the earlier ones this fall, you can still log on to that website and watch those lectures. Those of you who are with us in the auditorium and joining us by Zoom who are practicing lawyers in Texas, you do get 1 hour CLE credit for watching this lecture today, and the CLE course number will be available, and the QR code will be posted on the screen at the end of the lecture. So just stay tuned, and you can do it with your phone on the QR code, or you can otherwise get the course number from the screen or get it from me later if you just miss it altogether and just need me to email it to you. So just let me know about that. Those of you who are on Zoom, thanks for joining us. And those of you who are my students in Oil and Gas Law 1, remember, in order to get credit for attending today's lecture, you need to come down and sign my attendance sheet, which is down here on the third row between the two sections. So don't sign something else, sign that attendance sheet in order to get credit. Okie doke. So let me introduce our guest speaker today. It's Shane Walker. He's a professor in the Department of Civil, Environmental, and Construction Engineering here at Texas Tech. He's in the College of Engineering, and he's also director of the Water and Environment Research Center, acronym WATER, cutely enough, and the Texas Produced Water Consortium, which is primarily what he's here to talk about today. His research addresses some of today's most pressing challenges in water management, including advanced drinking water treatment, high recovery inland desalination, potable reuse, and beneficial reuse of desalinated produced water. He also teaches courses in water and wastewater treatment with a focus on physical and chemical treatment processes. He earned his bachelor's degree in civil engineering from Texas Tech, followed by a master's in environmental and water resources engineering and a doctorate in civil engineering from the University of Texas. Before returning to Texas Tech, he served as professor and director of the Center for Inland Desalination Systems at the University of Texas at El Paso. He grew up on a cotton farm east of Lubbock and has worked at a regional water treatment plant. So he has witnessed firsthand the importance of water for land and people, especially out here in West Texas. And he's taken on this grand task of trying to help accelerate research and development on how to put produced water, of which we have an endless supply in West Texas, to beneficial use in agriculture, irrigation, and even potable use in the future. So an amazing charge, and I think a doable charge, but it just requires a whole lot of intentional effort, and he's on top of the food chain doing that, and we're awfully happy and lucky to have him with us today. So please help me welcome Dr. Shane Walker.
Thank you, Bill. Well, thank you for the opportunity to present this afternoon. It's a real privilege to be here. I especially appreciate the privilege of being here at Texas Tech. A couple of years ago, I had the privilege of coming back home. My wife and I are high school sweethearts, and all our family lives here in the area. So it's a real privilege to be back in Lubbock and working here at my alma mater. Appreciate the chance today to connect with you in the legal aspects. Let me There we go. All right, so As Bill introduced, we got a great opportunity here in West Texas to take advantage of produced water. So I'll be talking about that today. A little bit of context for you. The Texas Water Development Board performs every 5 years a planning approach to water resources management across the state. That's broken out into 16 regions across the state of Texas. Region O is here local to Lubbock area. You can remember Amarillo is Region A and El Paso is Region E. And then we've got Region F below Region O, and that's the heart of the Permian Basin area. Just to give you some numbers in context here, you know, we've got over 30 million people now here in Texas and people moving here in droves. During the quarantine, people realized they don't really enjoy 1.5, 2-hour commutes. And so, hey, let's, move to the land of the plenty. So we got folks from California and New York, especially moving to Lubbock. Moving to of course, Lubbock's a great place to be, but to Texas. The state demographer estimates we're in the range of 1,500 people per day. So I grew up in a little town east of here, a little town called Crosbyton, about that size. So imagine one of those new towns every day. Or thinking about it another way, roughly 500,000 people per year. That's 2 new Lubbocks in the state of Texas every year. So interestingly, those folks that move to Texas are not required to bring with them their own water supply. They're not bringing a drop of water with them. So from a municipal perspective, since most people now in the state of Texas live in cities as opposed to rural areas, and that trend continues, there's a responsibility that the municipalities have to provide water for the people. And you could see Region O has a significantly higher expected water need than the other regions in West Texas. And that's due principally to irrigated farming, especially crops such as cotton. We've relied heavily on the Ogallala aquifer. And with declining aquifer levels, people are planning on how are we going to get alternative water supply for the crops that drives the economy, especially of this region. There are a lot of opportunities in Region F. You can see that in the last couple of decades, there's not been that similar expectation of water supply for crops. But with the opportunities of taking advantage of produced water, we could change that. So big picture, looking at 18 million acre feet per year demand for the state, based on 5 years ago, the most recent state water plan, expected needs of 5 million acre feet per year by 2030. So keep that number in mind. We expect we'll need at least another 5 million acre feet per year by 2030. Now, a lot of y'all know that the hydrologic conditions of Texas are set up east to west, with the eastern portion of Texas receiving significantly more rainfall than West Texas. Lubbock is kind of here in the middle, in the range of in the neighborhood of 20 inches per year, a little bit less on average. The eastern portion of the state receiving over 50 inches per year. And then, I lived in El Paso for 13 years, and we were averaging somewhere in the range of 8 to 9 inches per year. But one year we had 4.5 inches for the whole year. So very dry conditions. You can see from a surface water reservoir perspective, the state is well equipped from central Texas towards the east with a number of reservoirs, principally for municipal water supply. And we're sitting pretty, honestly, at about 75% full. But you'll notice there's a significant decrease in the spatial density of surface water reservoirs as you move west from about the Lubbock line. And most of those reservoirs in the western portion of the state are at really low levels. Elephant Butte Reservoir, which is actually in southern New Mexico, provides significant water supply for the El Paso region. That's down in the range of less than 5% full. And you go further down the Rio Grande to Lake Amistad and then down to Falcon Reservoir, percentages less than 25% full. So Ed Archuleta, the former CEO of El Paso Water, he would say 15% full should actually be said 85% empty. Not to be pessimistic, but to be realistic about our lack of surface water supplies. So the natural consequence of not having an abundance of surface water supply is to rely on groundwater. Now, I'm going to focus today on produced water, but I will also mention the Texas Water Development Board, through their BRACS program, has identified over 3 billion acre feet of brackish groundwater available across the state with salinity less than 10,000 milligrams per liter, which is about a third of the salinity of seawater. So energy efficient technologies such as reverse osmosis could be used to leverage those resources. But today I'm going to be focused on produced water. So many of you know the Permian Basin is the leading oil and gas producer in the United States and even globally. Almost 40% of the U.S. oil supply being led by the Permian Basin. The Permian Basin has two sub-basins, the Delaware sub-basin to the west and the Midland sub-basin to the east. The conventional drilling, was really focused on identifying pools, trying to discover pools of oil underground where you could just drill a vertical well and tap into that pool of oil and pump out that oil. With the advancements in horizontal drilling and hydraulic fracturing over the last couple of decades, the oil and gas industry has embarked on the unconventional oil development, where we're able to extract significantly greater volumes of petroleum reservoirs that are basically locked into the rocks. So hydraulic fracturing is basically leveraging water hammer to crack the shale formation and allow the oil to seep out. Now, interestingly, in the unconventional plays, especially in the Permian Basin and especially in the Delaware sub-basin, the water to oil ratio is anywhere from 3 to 5 barrels of water per barrel of oil. So the joke is the companies now operating are actually water companies with a lucrative byproduct. So the significant volume of water that's generated has to be managed. It has to go somewhere, because we're talking about over 20 million barrels per day of produced water. Well, that's too much to just send home with the operators in their pockets, right? You can't get rid of millions of barrels per day easily. It takes a strategy. So the companies have relied on saltwater injection wells, principally to dispose of that wastewater. In the Permian Basin, it's extremely salty, and so it's not immediately obvious that you would just put it to good use without some careful thought. You'll also notice that in Texas and New Mexico recently, several counties are really carrying the day in terms of increased oil and gas production. So there are several areas, especially in the northern Delaware sub-basin, that have been really productive, and a lot of the companies are focused on producing from that region. So let's talk through this diagram a little bit here. With the oil and gas activity, we're produced water. 15 years ago, a lot of that produced water was being hauled by trucks. Well, now the industry has moved away from that. That's too complex. So they've invested in pipelines, hundreds and even thousands of miles of pipe networks across the Permian Basin to convey the produced water that's being generated. So the produced water also in the industry has evolved where they realize now they don't have to rely on fresh water for the well completions. They are required by law to use fresh water for drilling. But then once you've got the well drilled for the well completion, for the hydraulic fracturing, their chemists have learned that they don't actually need low salinity water to perform that hydraulic fracturing. So they can reuse produced water. So the Permian Basin has shifted in the last several years to nearly be net positive in terms of water production. And I think that trend will continue over the next 5 years or so, especially with some lease agreements that were requiring groundwater to be purchased from the estate as well. As those come up for renewal, the companies no longer need that additional water supply. So I think that trend of relying on recycled produced water for the well completions will continue, and the basin as a whole will be a net producer of water. So what can we do with that water? Well, when the water comes up with the oil, you need to separate it. You probably also are aware that the Permian Basin has an enormous production of gas, so much so that in certain times and locations, it's a negative price paying people to take that gas away. So a great opportunity there as well. But then that water, if we're not going to recycle it for produced water, for subsequent well completions, it has to go somewhere. And so we've relied on injection wells, saltwater disposal wells, SWDs, to manage that excess water that needs to go somewhere. So deep well injection has been used. And when we say deep, the oil and gas industry is drilling deeper than 10,000 feet. So 2 miles, sometimes as deep as 3 miles deep. I've heard as deep as 15,000 feet. So 2 to 3 miles deep for injection wells. And until 2024, up through 2024, there were concerns with increased seismicity or earthquakes, especially, 3, 4, even 5.0 on the Richter scale. For those of you who were in Lubbock maybe a year and a half ago, you might have felt your pictures rattle on the wall with the effects of an earthquake in the Permian Basin. And what's been explained to me is that basically it's deep enough, it's near the faults and high enough pressure that produced water under those high pressures was effectively lubricating the fault lines and allowing more slippage, so basically facilitating more earthquakes. So the Railroad Commission implemented some seismic response areas, or SRAs, to limit the injections into certain zones that were identified to be more vulnerable to seismic activity. And based on the numbers in 2025, it appears that strategy has been effective, significantly decreasing the number of seismic events greater than 3.0 on the Richter scale. So that's good. The challenge, though, is that the operators, especially the midstream companies that are handling the disposal, have shifted to shallow injection. And now shallow, by oil and gas terms, is still much deeper than what we think of for agricultural and municipal production, in the range of 5,000 feet deep. So still a mile deep below surface. But some of the challenges there are overpressurization of formations that were historically not expected to be that high of pressure. So if you think about oil and gas wells that were previously capped, expecting pressures to stay less than a certain amount, and now we're increasing the pressure in those formations, there have been some issues with well blowouts. Previously capped wells that were just fine, but now with the higher pressures, they've popped off at the surface. I heard of one company that spent something like $90 million to plug a well that blew out. So when you're spending that much money on something, it causes you to take a step back and think, what's a bigger strategy here when we're investing close to $100 million in a single event? So well integrity. There's also a challenge with drilling through those shallow zones to get the deeper formations where the oil is. Now, some of the operators have reassured me that, they can fix that, correct that with just more robust well structure. So from a mechanical engineering perspective, we can solve that. I think there are two challenges that remain. One is the pre-existing oil and gas wells that were previously capped, some even abandoned, irresponsibly, that have a vulnerability of allowing salt water, this hypersaline produced water, to come back up to the surface. The other challenge is some geologists have estimated that in certain regions where we've been injecting a lot of the produced water, the pore space, kind of think of like an aquifer for water underground. If there's geologic formation that has some pore space that's open, we can inject the water there, but there's a finite capacity of that pore space down there. And so some people have estimated that in certain areas we've got less than 2 years of pore space remaining. Now then, there may be other formations that are further out that may have 10 or 20 years left of pore space available. But that's going to cost more to pump that water to a greater distance to manage the disposal further away. So some companies have estimated we're going to need to see investment of a couple of $2 billion in the next year and a half to implement the infrastructure required to manage this growing challenge of produced water. Now, once you start talking billions of dollars, lots of people are paying attention. So instead of spending billions of dollars to handle a waste, are there opportunities we could convert that into a resource? So Senator Charles Perry has been a visionary and a leader for water, a water champion in the state of Texas. He's from this area. He really appreciates the value of water, especially for agriculture. And so he led the development of the Texas Produced Water Consortium, established by Senate Bill 601 4 years ago, to be led by faculty at Texas Tech. So it's a real privilege for Texas Tech to be identified as the leaders in this area. Over the last several years, my predecessor and the team developed great collaborations, and we've really developed that now with a really diverse group of stakeholders and members, part of our consortium. So we've got upstream oil and gas, the midstream water handlers, landowners, agriculturalists, environmental stakeholders. We're also working in tandem with state agencies, especially the Railroad Commission, Texas Water Development Board, and then the Texas Commission on Environmental Quality. I'll talk more about that in just a second. And then also the Texas Parks and Wildlife. So really appreciate the work of those who came ahead of us and really established this. We've got a wonderful portfolio where people can really bring their resources, their ideas, their creativity, innovation, and also their concerns. And we can really think through how to manage this responsibly and come up with what I believe ultimately will be a more robust solution because we've got a diverse group of stakeholders involved at the table. So what could we do with that water instead of just disposing of it to deep well or shallow injection wells? What if we could use some kind of treatment method? That's what the TM stands for, to either technologies or methods, treatment. That's going to require some pre-treatment to make the water suitable for desalination, because there's a lot of salt in the water that really has to be removed. And then post-treatment polishing, which I'll talk about more in detail in just a second, with the trace organics or residuals that may still be in the water. Well, there are lots of opportunities if we could think about cleaning up this water. And I think a couple of years ago, people were really dubious, maybe skeptical that this water could even be treated. Now, I'm a technologist. I teach advanced water treatment systems. And so from a technology perspective, I have no doubt that this water can be treated, that we can build a treatment train, a sequence of unit processes that can take however bad water you can give us, we can treat it to whatever standards you want in terms of clean and safe. It is doable. Technically, it's doable. So one of the key questions that has remained is, can it be done economically? And can we prove that it will be done reliably and consistently so that the taxpayers can really benefit from this water resource. And so I'm excited to say over the last year and a half, there have been a number of companies that have been pilot testing different types of technologies. And we've seen several different treatment systems work. And two that I'll talk more about in just a second, but two other opportunities are irrigation of crops or rangeland restoration, so land application, or surface discharge. For example, augmenting the flow in the Pecos River. So to put this in numbers that other people might connect with, I grew up on a cotton farm, so we think about acres and we think about inches or feet of precipitation. So we think about acre feet per year. Coincidentally, that's also the framework that the Texas Water Development Board uses in their every 5-year planning for the state water plan. So thinking back about what I told you earlier, we're expecting we might need an extra 5 million acre feet for the state per year. If you look at this, if we could take that 20 to 25 million barrels a day of produced water, if we could recover half of that, why would we do half? Well, one, based on the treatment pilot testing that's been done, we've seen consistently between 50 to 60% recovery. So the fraction of the water that we get to keep as product water has been proven out to be 50 to 60% for most of these pilot tests. So that from a technical perspective, we believe it's feasible. The other is if you pull too much water out, you exceed the solubility limits of the minerals that remain in the water and you could precipitate solids. And if we want to continue using the saltwater disposal wells to manage that leftover salty water, then we don't want to exceed the solubility limits and generate solids that would then have to go to landfill. So we'll just keep everything soluble, keep it all in solution so that it's just a liquid discharge. So presumably we could recover half of the water as product water and the other half would continue to go to the saltwater disposal wells. But this would allow us to decrease by a factor of 2 the volume that we have to dispose in the wells. So one way to think about that is if we recovered half of that water, that would give us about 500,000 acre feet per year of fresh water. We could irrigate hundreds of thousands of acres of land with that much water. Now, this is a blue sky idea, I'll admit. This is a big picture. How are we going to distribute the water? How are we going to get it to fields? All those questions still need to be answered. We're working on that. But big picture, it represents a significant opportunity, a large opportunity to basically meet 1/10 of the state's expected water demand by 2030 with this single water supply. Another way to think about it is in millions of gallons per day. So a lot of the municipal drinking water treatment systems are rated in MGD, or millions of gallons per day. So on an annual average, the city of El Paso is a little over 100 MGD in consumption. City of Lubbock is in the 30 MGD range. So if you were to think about this in the framework of millions of gallons per day, 500 MGD is the equivalent of 5 El Pasos worth of water, or 15 Lubbocks of water. Remember I said in terms of population growth, Texas is growing like 2 Lubbocks every year. So this would give us a significant water supply towards meeting those needs. So a great opportunity. And from a legal perspective, from a policy perspective, how are we going to make this practical? Well, several years ago, that's what the Texas Produced Water Consortium was really focused on, and working with lawmakers to think about this practically. So the Railroad Commission has historically been in charge of managing the wastewater, that is produced water from the oil and gas industry. So several years ago, the state legislature transferred authorization of surface discharge permitting to the Texas Commission on Environmental Quality, TCEQ, our state environmental regulatory agency. Now, they already have effluent management for municipalities and other industries. So this basically put in the same regulatory framework or agency the opportunity to manage the permits for this specific oil and gas industry. And it's been a couple of years in development. TCEQ has developed some draft permits, and there are several entities that are working with TCEQ on negotiating those permits. And so I'm optimistic that in some months ahead that we'll see some advancement on that. And that'll be a really exciting point where the technology companies, the engineers, can then really design and fine-tune the design of the treatment systems to meet those regulatory requirements in terms of product water quality requirements. Now, the Railroad Commission a couple years ago developed what they called the pilot study framework for pilot projects of land application, which they still had jurisdiction over at that time. And so several entities have submitted and received approval for pilot study projects with Railroad Commission. Now, this most recent regular session of the legislature transferred authority of the land application permitting to TCEQ as well, effective September 1st. So really exciting now to see over the next couple of years, I expect those permits, TCEQ will go through its rulemaking process and make that permitting mechanism available as well. But in the short term, we've got several opportunities to work with some of the companies that received the pilot study frameworks, and I'll tell you a little bit more about that in just a second. So originally, the Texas Produced Water Consortium was focused on law and policy aspects of this beneficial reuse, and now we're really getting into the technical and economic aspects. So we've expanded the structure of our Produced Water Consortium with over 30 faculty here at Texas Tech. So our law, policy, and economics group is led by Amy Hardberger here of the law school, director of the Center for Water Law and Policy, and Ryan Williams, who's up at the vet school. He's an economist. And then Rye Malton is our project manager with experience in policy work in the legislature. And then we've got a surface discharge team led by Scott Collins in the Natural Resources Department of the Davis College of Agriculture, and Sung-Yu Park, focused on integrated surface groundwater hydrologic modeling. He's in my department in civil and environmental engineering. We've got a land application team led by Matt Seebecker. He's in the plant and soil sciences department with expertise on soil toxicity. Catherine Simpson and Caitlin Cooper-Norris working on different aspects of plants. And then we've got Krishna Jagadish, who's the director of the Davis College Water Center, providing support and leveraging support from that center as well. And he works closely with all the agriculture faculty especially. We've got a water quality and toxicology team led by Balaji Rao from environmental engineering, civil environmental and construction engineering, and then also Jordan Crego from our Department of Environmental Toxicology. So we're performing targeted analyses of known contaminants, non-targeted analyses with high-resolution mass spectrometry, where we can actually analyze for additional compounds that we don't even know if they're there. It's kind of like hunting for other compounds that might be present. And then in addition to that, we're performing effluent toxicity testing with regulated standard effluent toxicity tests, but also more advanced research methods with sublethal endpoints to evaluate the toxicity of the water and really confirm with those three methods, targeted chemical analyses, non-targeted chemical analyses, and effluent toxicity, to be able to confirm if the water is clean and safe. And then from a treatment technologies perspective, we're working in collaboration with the companies to help understand the treatment processes, and then also looking for opportunities to recover valuable materials from that produced water. You know, lithium's the hot topic these days, but there are other materials that might be present, cobalt, nickel, cadmium, that could have other industrial values as well. And then most recently, you heard last year from Doug Robinson from Natura Resources. We have the privilege of collaborating with them to study the synergistic deployment of small modular nuclear reactors. These are molten salt reactors developed by a company based out of Abilene, Texas. In collaboration, we're working with them to explore the synergy of that power generation system to recover waste heat for thermal desalination of produced water in the Permian Basin. And Marshall Watson is the department chair in petroleum engineering and director of the Oilfield Technology Center. So really have just a powerful set of expertise here at Texas Tech, and it's a really wonderful opportunity to engage in interdisciplinary research to really understand this technically and economically and help the industry and stakeholders advance this work. So real quick on salinity, the y-axis here is the salinity in total dissolved solids expressed in milligrams per liter. For reference, seawater is about 32 to 35,000 milligrams per liter, so at the bottom of this scale. So you can see in the Midland sub-basin, we're in the range, median range is in between 100 and 150,000 milligrams per liter total dissolved solids. And then the Delaware sub-basin is broken out here between the New Mexico portion, which is the northern portion of the Delaware sub-basin. I'm excited about opportunities in the southern or Texas portion of the Delaware sub-basin. We might be able to take advantage of ultra-high pressure reverse osmosis, which would be more energy efficient and capital cost affordable than thermal desalination technologies. So we're hoping to have a pilot scale system of that ultra-high pressure RO in the next month or so and do some testing to prove that out. So as I mentioned previously, we take produced water, run it through some pre-treatment steps, dissolved air flotation, especially to remove suspended solids, to take it into desalination. The industry has explored several different types of thermal distillation-based techniques. There's one company that's also looking at freeze desalination, different ways of taking the salt out of the water or take the water out of the salt water. And then with that product water that's left over, we need to do some polishing or purification steps to remove any trace organics, trace metals. I'm excited. We've done some preliminary testing in collaboration with Eurofins, a NELAP certified lab, third-party verification of the water quality data. I know you can't read these data on the screen, but the point is, this is just a snapshot of the over 700 analytes that have been evaluated in these different water qualities, pre-treated, desalinated, and then polished, desalinated, produced water. And it's not yet perfect. A couple of things that we've identified for surface discharge. There's some residual ammonia that we need to make sure we remove for to avoid toxicity for the aquatic organisms. And then on the land application side, it looks like we need to optimize the boron removal for crop production. In terms of land application, I'll show some pictures from our pilot site north of the Midland city. This is a really small plot, half an acre, but it's designed rigorously. 240 1 square meter plots where we're comparing rain-fed and irrigated plots, tilled versus no-tilled, and we're comparing several different types of plants. We've got native vegetation, cotton, sorghum, some seeded areas with native bunch grasses, and then another plant called guayule, which can be used to produce latex rubber. The U.S. has kind of been a deficiency of having its own domestic production of rubber and latex in particular. So here are just some pictures, show and tell from this season. We got a late start on planting, basically in August, but even just a month later, you can see a significant difference between the rain-fed on the right and the two irrigated on the left. And so whether it was irrigated with groundwater, that's the GW, or the polished desalinated produced water, PDPW, those irrigated plots did really well. And so far, it's just preliminary data. We don't see significant differences between the groundwater irrigation and the polished desalinated produced water. So really exciting to see plants growing. In terms of ongoing and future work, continue working with the midstream companies, especially some of the upstream, and then some of the technology developers on pilot testing produced water treatment, both the desalination and the polishing steps, extensive water quality analyses. That's one of the things that I feel like our role is really important as a third party, unbiased, research team to really confirm if the water is clean and safe. And which my technical bias is we just need to add more technology until we achieve that condition. Greenhouse and field trials, we're gearing up with Texas Tech's interdisciplinary research greenhouse to do extensive testing with several different types of plants and crops. With the surface discharge team, we're going to be baselining the conditions in the Pecos River. We've already had a team go out and sample water from several different points along the Pecos River, from Red Bluff Reservoir right at the New Mexico-Texas state line all the way down towards Amistad. The river has traditionally been brackish over the last 10, 20 years due to low flows. So this is an opportunity for the river to be receiving fresh water and really improve its quality and quantity. So really excited about what those results will show over the next several years. I mentioned critical materials recovery from produced water or the desalination brine. And then this, energy water nexus that we're kicking off in collaboration with Natura to explore the synergy between waste heat recovery from nuclear power for thermal desalination of produced water in the Permian Basin. And then continuing to work with our regulators to provide information and see how we can collaborate, help be a bridge, serve as a bridge. Ultimately, I believe we will be able to demonstrate that this water is clean and safe, that it can be used effectively and valuably, and that it'll benefit millions of Texans. And so we also need to be working on building public trust in the science and the technologies that have been developed. And so we've got a new group of faculty from AgCom to help us in engaging the public and monitoring what's out there on social media so we can be effective in education and outreach as well. So thank you very much for the opportunity to be here. Be glad to take questions. I think we got 7 minutes left. So thank you so much for the chance to present, and excited to hear your questions.
Questions in the audience? Can you use the little thing so the Zoom audience can hear you?
Is that good?
Yeah.
All right. I want to know, in your research, Texas has become a new hotbed for the development of data centers in the region. And so they're expected to use quite a significant amount of water. And I'm trying to do research on that. So I want to know, what have you guys found in regards to these new industrial users kind of coming into the space?
Yeah, you've identified another competitor for the water. The state needs to grow significantly in energy supply if we want to meet that demand for the AI data center opportunity. The other factor that you've identified is water. Now, a lot of the newer data centers, I think, are realizing that there have been communities around the nation that have been concerned with depletion of local water resources with some of the previous data centers that have gone in. And so I think the data centers are rapidly looking for opportunities to minimize or even eliminate the water consumption need. Most recently, in some of the discussions we've had, data centers are designing what they're calling closed loop cooling systems. So the processors now are so intense that they generate so much heat, they actually need liquid cooling. So they use a non-conductive fluid to pull the heat directly off the processors, and then that goes to a separate heat exchanger that could then go theoretically to evaporative cooling, which I hope data centers will avoid, instead of just using water to get rid of heat and evaporating that water away. I hope they can use air cooling. Now, air cooling does require more energy, which we're already short on, and it is more costly. But from a resource conservation protection perspective, I really hope that these data centers will minimize the consumption of water. They may use water in a closed loop for heat transfer, but I really hope they're not going to be using water in its evaporation to get rid of the heat.
Other questions? Shane, I've got one for you while we got a minute. What can you tell everyone about the economics? What can you tell them about current cost of disposing of produced water downhole versus what your target is to make it competitive?
Yes. Now, it really depends on where you are. Some of the folks are saying that produced water could be recycled and even disposed of for 10 to 20 cents per barrel. I think that's not going to last much longer. What I've heard in the kind of normal, typical range is in the range of 60 to 70 cents per barrel for disposal. Some people are expecting that in the next couple of years to rise to the $1 per barrel range. And meanwhile, this pilot testing that's been demonstrated over the last year and a half has some of the key leaders that we've been working with estimating less than $1.50 per barrel, some even as close to $1 per barrel. So in my mind, the cost curves are approaching convergence. And at that point, you know, it just makes economic sense to do it. But I think in the short term, there will be some early adopters that'll take the risk. I think they're going to see the best payout because they're going to get in on the ground floor. I think once the TCEQ draft permits are issued and there's actually confidence in that regulatory permitting pathway, there will be significant investment, probably hundreds of millions of dollars invested, if not, you know, in the magnitude of billions, to be able to take advantage of this opportunity to treat water to beneficial reuse.
And in letting the audience know just how broad and wide the participation is in the consortium, how many paying members are there in the consortium?
Right, do you know that off the top of your head? Almost 40.
And can you give them an idea of who all, you know, representative examples?
Super majors, you know, the major oil and gas upstream, midstream, land owners, agriculture organizations, municipal, environmental stakeholders. I mean, the full spectrum of people with a vested interest in seeing this realized in the Permian Basin especially.
Hey, those of you who are not in my oil and gas 1 class but are still interested in hearing more about this subject and have the availability, the class is at 2 o'clock today, 2 to 2:50 in room 106, and you're invited to join the students who are in that class if you want to hear more from Shane. But let's thank Shane Walker for being with us today.
Thanks again, Bill. Appreciate it.